nothing else than probability that y is greater than that. Because if we consider this probability and we divide our event, this event we divide into smaller parts, then we obtain that this probability is equal to the sum of these probabilities. So it is nothing else delta times the probability that y is greater than that. And we obtain what we need. So the expectation is here, and this formula is here, and it is the same. We can prove this inequality. Other case, when f, let f be the probability density function of y. So we can handle only these two cases. Either the random variable is discrete or it has a probability density function. And these two cases are exclusive cases. So it is not possible that the same random variable is at the same time is discrete and has probability density function. So either this or this. And these two cases are nuclearly exclusive. So we can handle these two different cases. And how can we calculate the expectation of a random variable for which f is the probability density function? We know that it is just the integral y times fy dy. So the integral value times density function and integration. But as y is non-negative, therefore its probability density function is 0 over the negative part of the line. So here it is 0. And here, so the shape of f is this. Here it is 0, here non-zero. Therefore, we can start the integration from 0, y, so this value is non-negative and this value is also non-negative. So if we omit a certain part of this integral, as our function is non-negative, so it will be less. We start the integration from delta, which is positive, from delta to infinity, y, fy, d. So it is smaller. And here, y is greater than delta. So we write less if instead of y, we write delta. Here it's a constant, so it is delta times the integration from delta to infinity fy dy. And what is this? Delta times, it is the cumulative distribution function. It was the probability density function, cumulative distribution function at infinity minus at delta. This from delta to infinity. Delta, delta, infinity. and it is equal to 1. 1, and this it is equal to the probability that y is less than delta. 1 minus this opposite event, it is the probability that y is greater than delta. The probability of the opposite event is 1 minus the probability. And finally, we obtain the same. The expectation is greater than this expression. It is the same as we wanted to show. So it is Markov inequality. There is another inequality which is called Chebyshev's inequality. There are different ways to write the name of Chebyshev. Markov and Chebyshev were Russians, and you know, in Russia they use what kind of letter? So for Cyrillic letters, which are close to Greek letters, and not Latin. Therefore, there are different ways to write Russian names with Latin letters.
Cyrillic.
Cyrillic letters. Sometimes you will find this, sometimes I don't know. There are different ways. For example, if you read an English book, it will be different as in German book. In Hungarian book, it is again something else. Chebyshev's inequality. Chebyshev's inequality. It is the following. Let x be a random variable. Let x be a random variable. Let m be its expectation, and assume that the variance of x is finite, and let epsilon be a positive number. So epsilon is a number. Then the probability that the distance of x and its expectation is greater than epsilon, this probability is smaller than the variance of x divided by epsilon squared. So it is Chebyshev's inequality. So if we know the variance of a random variable, then it is true that the distance of x and its expectation can't be too large. It is somehow close to its own expectation. So the Chebyshev's inequality shows that a random variable is somehow close to its expectation. The distance can't be too large. How to prove? Actually, we can use Markov's inequality. With the following variables, let y be x squared and delta be epsilon squared. Then inequality is the following. The probability that y is greater than, oh, might be it is not good. Might be it is not good. X minus m squared. X minus m squared. Y is greater than delta is smaller than the expectation of y over delta. But now, y is this. Y is x minus m squared. Delta is epsilon squared. And it is nothing else but the variance of x over epsilon squared. So this part is alright, you see, variance of x over epsilon squared. But what is this probability? We should show this. It is equal to y is x minus m squared, delta is epsilon squared. And this probability. Oh, it is almost the same, you see, almost the same. As
That's a square.
yes, as x minus m, the absolute value of x minus m and epsilon are non-negative. Therefore, it is this absolute value is greater than epsilon is the same as its square is greater than epsilon squared, because these numbers are positive. In the case of negative number, it is not true, of course, because minus 1 squared is plus 1, and therefore the inequality. So, for example, minus 1 is greater than minus 2. If I take the square, 1 is greater than 4 is not true. So for negative number it is not true, but for positive numbers this inequality is equivalent to this inequality. So it is Chebyshev inequality. And now we are almost ready to study so-called weak law of large numbers. We need a definition. The sequence of random variables y1, y2, and so on converges to y in probability or stochastically if for all positive epsilon the probability that yn minus y, the absolute value of yn minus y, greater than epsilon. So this probability goes to 0 as n goes to infinity. Actually, it is a good convergence. It means that this sequence goes to this random variable if their distance can't be too large. At least in probability, it means that the probability that this distance is large goes to 0. So this probability is small. So it's a good type of convergence. And now we are ready to state the weak law of large numbers. Weak law of large numbers. It is the following. Let x1, x2, and so on be pairwise independent and identically distributed random variables. Assume that the expectation they as they are identically distributed, their expectations are equal. So that we assume that the expectation of x1 is m, is finite, but m is the expectation of any of these random variables is finite. We should assume that this expectation is finite. Then x1 plus x2 plus xn over n, that is the average of these random variables, goes to m in probability. It means that the average of independent and identically random variables is close to their expectation if n is large. How to prove this result? The proof is quite simple. I write. Proof. What we should prove? This kind of relation, that is the probability that x1 plus xn over n minus m. So this expression minus this expression greater than epsilon, it should go to 0. But how can we calculate the expectation of this expression? Expectation as the expectation is a linear operation, it is the expectation of x1 plus expectation of xn over n. All of them are equal to n, n plus m. So it is n. It is the expectation. And what is the variance? What is the variance? So you see, it is the expectation. The expectation is here. The expectation of this expression is this.
Goes to the m.
N. M, it is n, besides n. What is the variance? What is the variance? Variance of x1 plus xn over n. The variance is not a linear operation, but if our random variables are pairwise independent, so the variance of a sum is the sum of the variances. So variance, because they are pairwise independent, x1 plus variance of xn, because pairwise independent, over n squared, because it is a rule when we calculate the variance. And we denote this variance by d. So it is n times d over n squared. It is d over n. Apply Chebyshev. Apply Chebyshev's inequality. Chebyshev inequality does the following. It is smaller than the variance of what? Variance of this. Variance of x1 plus xn over n divided by epsilon squared. But we use this. So it is d over n and 1 over epsilon squared. And this part goes to 0 because 1 over n goes to 0. You know 1 over n goes to 0. This 1, 1/2, 1/3, epsilon. It goes to 0. So, actually, we were able to prove the law of large numbers. Weak law of large numbers is not very difficult, but not very simple. But we were able to prove this theorem. There is another law of large numbers, which is called, actually this proof, we prove only if the variance of x is finite. It's enough. If the variance is not finite, the proof is difficult. But if the variance is finite, the proof is simple. But you see, we have only weak law of large numbers. And there are strong law of large numbers. It is the following. We need a definition. we need a definition. Yn goes to y almost surely. Surely. It means that with probability 1, so 100%, probability 1, it is 100%. If the probability that Yn converges to y is equal to 1. So the probability is 100% that Yn converges to y. It is a stronger convergence. This convergence is stronger than convergence in probability. This convergence is stronger than convergence in probability. So strong law of large numbers. Strong law of large numbers. It is the following. Actually, this theorem was proved by Kolmogorov. It is so-called Kolmogorov's strong law of large numbers.
Russian.
Let x1, x2, and so on be independent and identically distributed. Random variables, and assume that the expectation is finite. Then the average x1 plus xn over n goes to m almost surely. You see, the two results are almost the same. Here in the weak law, these random variables are pairwise independent and identically distributed. Here they are not pairwise independent. We can say that totally independent, but it is not important. Total independence is stronger than pairwise independence, but I will explain later. What is important? We have random variables. They are independent and identically distributed. In the case of weak law, this average goes to the expectation in probability. In the case of strong law, the same average goes to the same value, that is the expectation, almost sure. So that these two theorems are almost the same, but here this convergence is stronger convergence. We can't prove this result, it would be very difficult for you. But I mentioned something. Etemadi, he was not Russian. Etemadi, I think he's an Iranian guy, Etemadi, but living in United States. He proved, Etemadi proved, later on, proved Kolmogorov law, this Kolmogorov law, assuming only pairwise independence. Pairwise independence. I mentioned these results in this way because usually people know Kolmogorov's law of large numbers. Most people know Kolmogorov's law of large numbers, this law here, and they don't know Etemadi's result. Therefore, I should mention that what is well known and written in textbooks, this law with total independence. But actually, it is true assuming only pairwise independence. But most people and most textbooks don't know this result because it is not very old result. It is much older result. Why is it important? Why is this result important? I mentioned a quite famous consequence. It is the following. Maybe you remember that when we introduced the probability was something else as relative frequency. For example, if